All right, so Unit 5, chemical bonding. Your learning target, so by the end of this unit, you should be able to define what a chemical bond is and why we form chemical bonds, differentiate between ionic and these different types of covalent bonds, construct electron dot diagrams, you already know how to do that, and Lewis structures. List the properties of an ionic versus a molecular compound. Explain properties of metals based on their bonding. That's what we're going to do today. Predict the shape of molecules or ions using Vesper theory, and explain the 3 types of intermolecular forces. So lots to cover in a short amount of time. As always, here are vocabulary words you will be hearing me talk about. I don't require you to go and define these, but if you don't know what a word is and you keep hearing me say it, then you better go look it up. If I keep on saying octet rule and you don't know what octet rule is, then you better go look it up. If you don't know what a dipole is, then you better go look it up. All right, so today, metallic bonding. So there's 3 types of bonds we're looking at. Today we're looking at metallic bonding. So metallic bonding, what do you think it has to do with? Oops. Metals. Oops, sorry.
Come on, Miss White.
I know.
There you go.
Bonding. Metallic bonds. Has to do with metals. A metal bonding to a different metal. So zinc bonding to copper to make brass, or a gold ion bonding to a gold ion bonding to a gold ion. All of these are properties that they are going to have. So they have high conductivity. What does conductivity mean? They conduct electricity. So if these are highly conductive, then that means they're going to be good at conducting electricity. So metallic bonds. So if we have metallic bonds and you want to know some properties or what are the characteristics of metallic bonds, they have high conductivity. Now, why do they have high conductivity is because they have what we call highly mobile valence electrons. So what does mobile? If something's mobile, it moves. So these, and where are valence electrons? Outer shell. So these electrons in the outer shell are moving from one atom to another. And we refer to this as a sea of electrons, or the electron sea. So these are nuclei. All right, so each one of these pluses is the nuclei. This round part right here, that is showing the valence shell. And then you see all these little negative signs. Those are the electrons in that negative shell, or in that outer shell. They're moving. At one point, this electron may be here, and then it may move its way all the way to become down here next to this with this atom. And then it may move and be with this atom. Yes? It's a valence shell. So these electrons are continuously moving from one atom to another. And we're going to watch a video on this. Questions on that? So you should be able to draw that C and know what is going on. Okay, so these are roaming freely from one nuclei to another. And we call these delocalized. Delocalized electrons. delocalized, and those are the valence electrons. So they're not committed to staying with one nuclei. They're going from one to another to another. So these delocalized electrons, they have to deal with the conductivity, like we just talked about, and of metals, and they have to deal with the luster of metals. What's luster mean? Shiny. So metals are shiny. And that's because these electrons are moving from one atom to another, and while they're also moving, they're also gaining energy and losing energy. And when they lose that energy, it comes off in that form of that shine, that light we see. So, excuse me, conductivity and luster. All because of the sea of electrons. Questions on that? You guys need a second before I move to the next slide? Here we go. And lastly, the ability of the metal nuclei, so those positives, what happen is they ride over, think of this as the sea of electrons, and they're sea of electrons, and these metal nuclei are riding over that sea. And what happens is we are able to have ductile metals. What's ductility mean? If something's ductile.
That's
I think it's duct tape.
shiny,
Ductile, isn't that like
bendable.
I'm gonna say
Strings? Strands?
Wire.
Ductility is to pull metal into strands, or in other words, wire. To pull the metal into strands. And what about malleability? What does malleability mean? Bendable, hammered into shape. Okay, so the four properties of metallic bonds, all because of the electron C, are highly conductive, luster, ductility, and malleability. Are we passing notes?
Yes, probably in the 6th grade.
read them this
I am.
You could read it. It's not that interesting.
Why are you talking to your class?
They're talking mess about you.
Talking mess about me?
Read the notes.
Well, you know what I could say, though? At least they were in class on Friday.
See, that was me. That was me.
Oh, I get it.
At least I was in.
She just wants to go home.
It's okay.
You had to pass a note to say you want to go home?
I was gonna come to class, but then they told us we were gonna get ISS, so I just told mom to pick me
That's
up.
why
That's why you're not mess about me.
And that's why he's going to get up and go pick it up.
Oh, YouTube. That's right. That's right. I'm supposed to not drown.
Should I go pick that up?
I don't know. What do you think?
My bad.
Okay, so we are going to watch a video. It's next time. It's recite it for me. Put the date on there. Okay. All right.
Speaking of that, what did we do on Friday?
Dude, that was like a week ago. I'm sorry.
Took a test.
Did we really?
Yep. Test.
Okay. You guys got to focus. I'm recording and
Okay.
we are going to watch a video. It's about 7 minutes long over the sea of electrons and metallic bonds. If I were you, I would be taking notes because at the end you're going to have to write 2 to 3 sentences over each one of those and what is going on in the metallic bond. And then be able to draw it and explain it.
What?
What?
And explain? Hold up.
Okay.
That's a 2 sentences.
Wait, so we have So we have to write 2 sentences like over the video?
Not over the video, over the of each one of these things he talks about.
Oh.
Okay.
Who said it?
Okay, this is a tutorial on metallic bonding, and we're going to be looking at the electron C model of metallic bonding and how that can explain such properties as malleability, conductivity, and luster. So the properties of metals can be understood by looking at the atomic structure of metallic bonding. But first, let's get reacquainted with the ionic bond, because if you understand the ionic bond, that's going to make it a lot easier to understand what the electron C model is telling us. So here we have a metal reacting with a nonmetal. The transfer of the electron, the reaction, results in a positive ion and a negative ion. So the ionic bond is simply the electrostatic attraction between the positive and negative charge that the ions have. So you could call this a sodium atom and this a chlorine atom, and once the sodium loses an electron, it becomes Na+, and the chlorine gains that electron and becomes Cl-. So the sodium ion and the chloride ion, being oppositely charged, are electrostatically attracted. And so that opposite charge results in a crystalline structure where we have an ongoing array of alternating positive and negative that are all attracted to each other, and that keeps the crystal together. Let's look at the arrangement of atoms in a metallic crystal. Very similar to the organization of an ionic crystal, however, they're all positively charged. And just looking at this illustration, you would think that the atoms would completely fly apart by repelling each other due to the positive charge. But if we take a closer look, the electron C model tells us how the positively charged cations in the metallic crystal can stay together. So as an example, we'll take a look at aluminum. Looking at the subatomic structure, we can see each aluminum atom has 13 protons, but only 10 electrons. It has given up the 3 valence electrons to what is called the electron C. This is why it's called the electron C model. The space in between each atom is filled by the valence electrons that have been given up by each metal atom. So the metal atoms become cations, positively charged ions, and the valence electrons are loose in the spaces between the cations. So what's holding the crystal together is the electrostatic attraction between the positively charged cations and these free-floating negatively charged electrons. And so the valence electrons are not localized to any one particle. They are free to move and occupy the space between the positive ions. And so similar to the electrostatic attraction that holds the ionic crystal together, we have this attraction of opposite charges that are holding the metallic crystal together. So aluminum giving up 3 electrons means that all the cations have a 3+ charge, and each aluminum atom has contributed 3 electrons to the sea of electrons. This creates quite a strong attraction, and we can use this model as a way to explain various properties. For example, there is malleability, the ability to put pressure on a piece of metal and not have it break. So we can pound metal with a hammer, we can pound it into a shape and not have it break. How can this model explain that phenomenon? Well, let's hit it with a hammer and see what happens. Ooh, one last blow. Okay. So as you can see, the atoms were shifting. They didn't break apart. Hitting the metal with a hammer does not break it. Why would that be the case? Well, the delocalized electrons are always there. So any shifting positive ions are going to be able to be held together by their attraction to the constant presence of those valence electrons, that sea of electrons that the atoms are attracted to. And malleability, of course, is also intimately related to ductility. You can force the metal into the shape of wires. So this is malleability. And a nice contrast would be to look and see, why does hitting an ionic crystal not result in this sort of malleability? When we hit an ionic crystal, it shatters. Let's hit this ionic crystal with a hammer and see what happens. So no matter how you hit it, you're always going to come to some point where like charges are lined up. And so if like charges are lined up, the result is going to be a great deal of repulsion, and that's going to split the crystal. And when ionic crystals cleave, they often leave a very sheer, smooth face if you do it carefully because of the way the opposite charges line up. All right, back to metallic crystals. So why would this very strong attraction result in other properties? How about their strength and high melting point? Well, the atoms want to stay together. They're very attracted to the sea of electrons. And so, therefore, the higher the amount of valence electrons given to the sea of electrons, the tougher the metal, the harder it is, and the higher the melting point. Transition metals in particular, like titanium and molybdenum, each of which contribute a large amount of valence electrons to the sea, they are very tough metals, very strong, very high melting points. How about electric current? Can this model explain that? Well, electric current is simply the movement of charge. And electrons are constantly moving through these spaces between the cations. They therefore are very able to carry an electric current. And that also explains their heat conductivity, the fact that they can move through the crystal. And what about the shininess, the luster of metals? If you think about where light comes from, the emission of visible light from electrons, well, the sea of electrons, these valence electrons, can very readily absorb and re-emit visible frequency photons, and that makes metals very shiny, very lustrous. And so here's an example of a giant structure, a sculpture in Chicago called the Bean. It's extremely shiny. It's made out of stainless steel. It's primarily iron, chromium, usually a little bit of nickel, definitely some carbon, and depending on the stainless steel, a few other metals thrown in, all engaging in metallic bonding. So the shininess comes from the ability of the stainless steel to easily absorb and re-emit visible spectra of light. But what's interesting about that is if you think about what would happen if you put a scratch in the bean. Well, you would see that scratch because it would scatter light. So it would no longer be shiny right where the scratch is, right where there's an irregular surface. And an irregular surface will scatter light in different directions. So the shininess of any metal does depend on how smooth the surface is. If it's a scratchy, non-smooth surface, then you don't get that shininess.
Okay. Let's see.
This way, how did the lights just come on?
What?
Oh, I thought somebody walked over there. Oh, the devil's alive.
What?
Y'all know how to play with spirits. How did that go?
I walked over there 5 seconds ago.
Right here?
Over here.
Oh, right there. I'm about to say,
Okay. So what you need to do now is the following. In your notes. For each of these properties, you need to draw the electron C and write 2 to 3 fully developed sentences explaining why explaining the reason for the conductivity. Explain what's going on for the malleability and what's going on in ductility. And then we are going to discuss that. So I'm going to give you guys about 7 minutes to work on that, and then we're going to discuss it.